कर रहे शूटिंग चल रही अच्छा हाँ next problem it's given a monkey climbs a pole of height 15 meter okay in 1 second it moves up by 3 meter and very next second it slips by 2 meter. It repeats this okay for every second it moves up by 3 meter then next second slips by 2 meter. It goes on. At what time monkey will be at the top of the pole? Normally what some of those friends will do is in 1 second moves up by 3, in next second slips by 2. So finally 3 up, 2 down, it's 1 meter up at the end of 2 seconds, right? So for every 2 seconds monkey moves up by 1 meter. Is it clear? Something like that. So if you go by the same logic, for 15 meter it needs 15 into 2, 30 seconds, but that's not the answer. Okay, as some of you might have already guessed it. Okay, this happens only until the height of 12 meters. Okay. 3 up, 2 down, 3 up, 2 down. That means every 2 seconds 1 meter, every 2 seconds 1 meter. So for 12 meter, 12 into 2, 24 seconds already gone. Now, next second, monkey will move up by. अरे वो हिलता, तुम करो ना कहीं को नहीं कर रहे? शूटिंग चल रही अच्छा हाँ next problem it's given a monkey climbs a pole of height 15 meter okay in 1 second it moves up by 3 meter and very next second it slips by 2 meter. It repeats this okay for every second it moves up by 3 meter then next second slips by 2 meter. It goes on. At what time monkey will be at the top of the pole? Normally what some of those friends will do is in 1 second moves up by 3, in next second slips by 2. So finally 3 up, 2 down, it's 1 meter up at the end of 2 seconds, right? So for every 2 seconds monkey moves up by 1 meter. Is it clear? Something like that. So if you go by the same logic, for 15 meter it needs 15 into 2, 30 seconds, but that's not the answer. Okay, as some of you might have already guessed it. Okay, this happens only until the height of 12 meters. Okay. 3 up, 2 down, 3 up, 2 down. That means every 2 seconds 1 meter, every 2 seconds 1 meter. So for 12 meter, 12 into 2, 24 seconds already gone. Now, next second, monkey will move up by 3. It's already at the top. Slipping doesn't matter now. So in 25 seconds, monkey is at the top. Fine. Next problem, it's given a bullet fired with a velocity of 500 meter per second in series of 3 planks, okay, made of same material. It loses 100 meter per second velocity in each plank. Ratio of the thicknesses of the planks. Ratio of thicknesses of the plank. It's fired with 500, okay, here it loses 100 means become 400, 300, 200. What we do is, we'll add 2 more planks here for convenience. And suppose it's losing another 100 here and another 100 here. So it will come to rest here. We need the ratio of thickness of these 3 planks, not these red ones. Fine. Okay, we know material is same means deceleration is same. Change of velocity by time is deceleration. Change of velocity in each plank is same and deceleration is same. So time spent in each plank is same. We know when a body is starting from rest and moving with uniform acceleration, ratio of displacement in successive equal interval of time when it is accelerating it's like this. Like for example, if you drop a body, ratio of displacements, height of fall in successive seconds will be in the ratio 1:3:5:7. But when you project it upwards and finally suppose the body comes to rest at the end of 4 seconds suppose. Then here, from top it is 1:3:5:7. Okay, from bottom if you take it will be 7:5, decelerating case, right? Finally it should be 3:1. Is it clear? The reverse thing. Here the same thing is happening. Fine. The bullet is finally coming to rest. Okay, so it's spending same time. Time is same because change of velocity in each plank is same, deceleration same. So when these two are same, time has to be same. Spends equal time in each plank. So in equal time, uniform deceleration means, okay, from the other side it will be 1:3:5:7:9. We need ratio of the thickness of these 3 planks. The answer should be 9:7:5. Clear? Now, it's given 2 cars A and B are moving with equal velocity and they are at the same place initially. This fellow applies brakes and stops after covering displacement test, decelerating at uniform rate. Okay, what will the displacement of car be at that instant? Obviously it will be 2s. It's pretty simple because here velocity is v, here it's 0, average velocity is this, average velocity in time is displacement. For this, its velocity is constant, so average velocity is v. So it will be vt, vt is 2s. Is that clear? Similar problem, here car A and B are at the same point. Car A is starting from rest with a constant acceleration and car B is going with a constant velocity v. Okay, so obviously initially car B will be moving at, then this car A accelerates and crosses. Okay, when they meet once again, at that instant what will be the velocity of car A? Okay, pretty simple once again. Here they are starting at the same time, they are reaching at the same time. So total displacement is same, total time is same. So that means average velocity is same for both. And we know very well, for this particular car, average velocity is b because it's moving with a constant velocity. When something is constant, average value is equal to that constant value. Fine. So its average velocity is v. For this car as well, average velocity should be v. But here it is 0. So 0 plus this whatever v dash, if I call it, that by 2 should be v because average velocity should be same for both cars. So v dash should be 2v. Is that clear? It's pretty simple. You can just think of it. See, the 0 should be 2v, so that average is 0 plus 2v by 2. That is v. Fine. Next problem. Suppose a body is projected at an angle theta with initial speed u. What is the average velocity for the entire journey? We know the body starts from ground and reaches the ground. So average velocity in vertical direction is 0 because vertical displacement is 0. Fine. So whatever average velocity we are going to take, it will be only in horizontal direction. And we know for a projectile, horizontal component of velocity, that is u cos theta, remains constant. Fine. So when something is constant, its average value equal to that constant value. So average velocity for this projectile for the entire journey is u cos theta. In vertical direction, average velocity is 0 because there is no vertical displacement. In horizontal direction, velocity is constant. So average velocity for the projectile for the entire journey is u cos theta. If you want to do in a systematic way, you can definitely take total range, that is displacement by time of flight. You would still end up with u cos theta. Fine. That's average velocity for the projectile for the entire journey. Now suppose if a player kicks a football with a velocity u at an angle theta to the horizontal, with what velocity the player should run so that the ball always remains over his head? Obviously, you know, when the ball is here, player should be here. When the ball is here, player should be here. Ball is here, player should be here. When the ball is here, player should be here. And you just catch the ball. The ball should always remain as over his head. That means both should have the similar horizontal motion. Both should have similar horizontal motion, similar horizontal motion, similar horizontal motion. Alright. Because horizontal motion, they are not, the boy is not feeling it. Player is not feeling it. We feel only differences. Fine. So obviously, the ball is going with a constant velocity u cos theta in horizontal direction. Even player should go with the same velocity. So velocity of the player, so that the ball always remains over his head, is u cos theta. Fine. Okay, next problem. Suppose it's given like this. A body is projected at an angle theta with speed u. Okay, until it reaches the topmost point, what's its average velocity? Okay, some of the students might try to do like this. This is h max, and until it reaches h max, horizontal displacement is r by 2. So this is the net displacement. Net displacement by time of, ascent, that will give you average velocity. Definitely that is the correct method. You will end up getting correct answer if you do proper computations. But then that's very lengthy method. The simplest method to do this is, we know in horizontal direction, velocity is constant, that is u cos theta. So average velocity in horizontal direction is u cos theta only. Alright. And when it comes to vertical direction, we know initial velocity here in vertical direction is u sin theta. And at the topmost point, vertical velocity is 0. So in vertical direction, okay, average velocity is this plus this by 2, because you know very well here deceleration is constant. When acceleration or deceleration is constant, average velocity is u plus v by 2. In vertical direction, you can safely write average velocity as u sin theta by 2. And when you know this velocity is u cos theta average value and this is u sin theta by 2, net average velocity for the journey until it reaches from here till the topmost point is under root this squared plus this squared. Alright, so common term is u, I'll take out u common. Alright, so what is left out is, this is sine square theta by 2 squared is going to be 4 here, plus cos square theta. Fine. Take LCM and that will be 4 ends out, that will become 2 here. And here you have sine square theta plus 4 cos square theta. 1 sine square plus cos square is 1. Another 3 cos square theta will remain there. So this is the answer, average velocity until it reaches from the point of projection till the topmost point. Fine. Next problem. It's given bullets are fired with equal speed v0 in different directions from a given point. What's the maximum area on which the bullets will spread on the ground? Fine. Okay, here a bullet is fired with velocity v0. The maximum distance in a given direction will go is the max range, and that will be when it's fired at 45 degree. Sine 2 theta is 1, and this is the maximum range. In each direction, that's going to the maximum distance. Okay, each side it will go maximum v square by g, v square by g, v square by g, v0 square by g, v0 square by g, v0 square by g. Fine, from a given point. So it is a circle whose area is equal to pi into r square. This max range will become radius. So that's become pi v0 power 4 by g squared. That's the maximum area on which the bullets will spread on the ground. Fine. Next problem. It's given a bullet is fired at an angle of 69 degree to the horizontal with a velocity of 107 meter per second. What is the change in velocity of this bullet in 4th and 6th second of its travel? Okay. The moment you see change in velocity, we should remember something where we use this to define. That is the definition of acceleration. Go to basics. Don't think high, just go to basics whenever you have doubt. We need change in velocity. And change in velocity is acceleration into time. Acceleration is g in this case. It doesn't matter what is the initial velocity and what is the angle at which it's projected. Acceleration is g. So change in velocity is basically g into t. Whether it is 4th and 6th second, when 4th second is 1 second, 6th second is another 1 second, so put together they are 2 seconds. In fact, it could be change of velocity in any 2 seconds, it is going to be g into 2, that will be 19.6 meter per second vertically downwards, because change in velocity will be in the direction of acceleration, which is down. So this is the change in velocity in 4th and 6th second, or in fact in any 2 seconds of a projectile. Next problem, it's given a body is projected at an angle theta to the horizontal with initial velocity u. Okay, at certain point p in its path is found to move at 90 degree to the original direction. Its velocity at point p is. Okay, horizontal component of velocity should remain constant. In fact, this velocity is given initial velocity, which is u at an angle theta above the horizontal. Okay, here let the velocity be v. We need to find out this v. Okay, it's given this velocity is at 90 degree to the initial velocity u. If this angle is theta, this angle will be 90 minus theta, and horizontal component should remain constant. Here it is u cos theta. Okay, that u cos theta should be equal to v cos 90 minus theta. Okay, u cos theta horizontal component. Here if the velocity is v, its horizontal component will be v cos 90 minus theta, and cos 90 minus theta is sin theta, so this becomes v sin theta. In fact, we need this v, so that will be u cos theta by sin theta is going to be u cot theta. So that's the velocity at that point, okay, when velocity becomes perpendicular to the original direction of projection. Fine. In the same problem, if it is asked time taken for velocity to turn through 90 degree, fine, we need time. Okay, now velocity is completely turning through 90 degrees. Suppose it's happening at point P, so this angle is 90 degree. Okay, so we know entire velocity has turned through 90 degree, means velocity's component in the original direction is 0. That means in this direction velocity should become 0. Let us take this as x-axis and this as y-axis. We want time for velocity in x direction to become 0. Alright, we know acceleration is g in this direction. This angle is theta, means even this angle will be theta, and this angle what we need, this particular angle is going to be 90 minus theta. Okay, so acceleration's component in x direction, this acceleration, okay, g cos 90 minus theta is g sin theta. Fine. And we want velocity in this direction to become 0. Just in this direction apply the equation. Deceleration, because it is in opposite direction to velocity. So velocity in this direction should become 0, because entire velocity turns to 90, means component of velocity along this direction is 0. V equal to u minus at. We are using v equal to u plus at. In fact, a is minus g sin theta into t. So from this we need t. So t is basically u by g sin theta. Is that clear? Let's do this problem by a different method. We know acceleration due to gravity is downward. So this is velocity. And okay, initial velocity. Velocity at time t is given by v equal to u plus at, where u and g are in appropriate directions. Okay, so now we know the angle between g and u is 90 plus theta. This 90 plus theta. Alright. Okay, it's given velocity should turn through 90 degree, means the angle between initial velocity and final velocity at that particular point P should be 90 degree. That means the dot product should be 0. That means u dot v should be 0. That means u dot v is basically u plus gt. This should be 0, right? Dot product should be 0. We know u dot u is u squared, and u dot g, t is as scalar, doesn't interfere. So u dot g means this is u and this is g. Angle is 90 plus theta. So u dot g is mod u mod g cos 90 plus theta is, you know, cos 90 plus theta is minus sin theta, and this t as it is. Fine. So this should be 0, because u and v are mutually perpendicular. So bring this side, you will end up getting the same value for t, t as u by g sin theta. This was second method to do this problem. This problem can be done by another method like this. Okay, we need time taken for velocity to turn through 90 degree. We know time is going to be change in velocity by acceleration, by definition of acceleration, alright. So, okay, we need change in velocity, and change in velocity by definition will be v minus u, means v plus of minus u. Initial velocity we need to negate it. This initial velocity, let me just negate it. So this is minus u, just reverse the direction. So this is minus u. Okay, now tail, head, resultant, head, tail. So this is going to be change in velocity vector. Alright, so this change in velocity, okay, we know now. This is theta, this is 90 minus theta, so this angle will be theta. Alright, and we know in a simple triangle, if this particular angle is theta, this vector is a, then this is going to be a sin theta, opposite side, right angle triangle. Alright, but then if this particular side is a, then hypotenuse is not going to be a sin theta, rather it's going to be a by sin theta. Fine, because this then becomes a by sin theta into, you know, a sin theta, sorry, because then this side becomes a by sin theta into sin theta, which will be a. Fine. Now we know this magnitude wise this is u, this is theta, this is opposite side is u, so this change in velocity which is hypotenuse, that becomes u by sin theta. So this change in velocity is basically u by sin theta, okay, and g as it is, so u by g sin theta, time taken for velocity to turn through 90 degree. Fine. There are at least 3 more methods to do this problem, okay, but I'm not going to show that, okay, these 3 are more than enough. Let's now discuss the motion of a horizontally projected body. Suppose a body is projected horizontally with a velocity u from the top of a tower of height h. Okay, horizontal velocity u will remain same throughout the journey. Even when it is about to hit the ground, it will remain u. Coming to vertical part of the horizontal projectile's motion, initial velocity in y direction is 0 because entire velocity is horizontal, u cos 90 is 0. Acceleration in y direction is g. I am taking downward direction positive. It was at this horizontal level. By the time it hits the ground, it will come to this horizontal level. So in vertical direction, this is the displacement h. Fine. This distance, this is displacement. We don't need all that. We just need vertical displacement. That is h by the time it hits the ground. Fine. So displacement in y direction is h. The time it takes to hit the ground. Before getting this, let's compare its motion to the motion of a dropped body. For a dropped body, initial velocity 0, acceleration g down, taking downward direction positive. Displacement h by the time it hits the ground. Times 0gh, 0gh, there is no difference at all. So what we can safely say is vertical part of the motion of a horizontal projectile, vertical part of the motion of a horizontal projectile is just like the motion of a dropped body. So over here we know time of fall for a dropped body is going to be root 2h by g, and over here also it should be root 2h by g. That means time of flight or time of fall of this horizontal projectile just depends on vertical motion, is independent of this horizontal motion. Even if this horizontal velocity u, even if this horizontal velocity is 2u or 3u, doesn't matter because here it is independent of u, just depends on height. Okay, so somehow this is the time at which it hits the ground. Now coming to the velocity in y direction, I mean with what vertical component is going to hit the ground. For a dropped body, velocity with which it hits the ground, we already know, we have obtained that earlier, it is root 2gh. And now over here the vertical component of velocity will definitely be root 2gh. Just like the motion of a dropped body I told you, vertical component will get the same. What about the entire velocity? Obviously entire velocity is this. This is u, this is root 2gh, this is going to be under root this squared plus this squared. So the velocity with which the projectile, horizontal projectile is going to hit the ground is root over u square plus 2gh. And this is in fact going to be the velocity with which a projectile will hit the ground, whether you project it horizontally or in any other direction with equal speed u. Same speed u. In all possible cases it will hit the ground with the same final speed. You can get that using law of conservation of energy. Fine. P plus k constant. Here you take P to be 0 and here half m u square plus mgh equal to half m v square. You will get this v as this. Fine. Okay. But then time which we took it as, in fact we derived it as root over 2h by g. Okay, that is valid only for a horizontally projected body or for a drop body, but right now we are discussing horizontal projectile. So forget about the case of a drop body. Fine. So anyway, we got, okay, initial velocity in y direction was 0 and acceleration in y direction was this, something like this. Fine. So velocity is this. Fine. Alright. And at what angle? Suppose it is hitting at an angle theta to the horizontal. This root 2gh you can safely shift the other side, translate it and keep it here. And now you can safely show tan theta is this by this, or theta is tan inverse of that. Fine. Tan inverse of root 2gh, that is vertical component, by horizontal component. This particular angle to the horizontal, it is going to hit the ground after so much time and with this particular speed or velocity. Fine. Okay, next problem. Suppose two bodies are projected, one up and other down with equal speed u simultaneously. What is going to be the time difference in their hitting the ground? Okay, we know this body is going to take 2u by g to come back to the same level, 2u by g, alright, and when it comes back, it will have the same speed u. Okay, the body which is thrown down, suppose if it is taking time t1, further time this body takes is also going to be t1, further time, so extra time is this, so that's going to be the time difference in their hitting the ground. And, okay, in the same question if it is asked, what's going to be the separation between the two bodies t seconds after projection? I mean, both bodies are projected, one up and other down simultaneously. Okay, so what's the separation between them t seconds later? We know acceleration is g for both the bodies, relative acceleration 0, relative velocity will remain constant, relative velocity is u minus of minus u means 2u. Okay, that 2u will remain constant. So relative separation between the two with respect to each other, they'll be how far apart? Relative velocity into time, because there is no relative acceleration. 2ut apart t seconds later. Almost similar problem. Two bodies are projected simultaneously with equal speed u, one theta above the horizontal, other theta below the horizontal from the top of a tower. Okay, what's the time difference in their hitting the ground? Okay, just over here, time difference is 2u by g, we have seen. And time depends only on vertical part of the projectile motion. Over here, vertical component of velocity is u sin theta. This one will have a downward component equal to u sin theta. So, okay, instead of u, we are having u sin theta here. So, time difference in hitting the ground is going to be 2u sin theta by g. Okay, this is the time difference in the two stones hitting the ground. Alright, now, what is the distance between the 2 points where these stones hit the ground? Okay, this stone, okay, is going like this, suppose, and hitting the ground. This will go like a, okay, and will hit the ground here. We know this angle is theta, even this angle will be theta. And at the same level, speed is u, means over here also, speed is going to be u. Fine, at an angle theta. Further motion of this projectile is just like the motion of this projectile. Theta below the horizontal u, theta below the horizontal u, further motion is similar. In fact, this horizontal displacement covered is equal to the further horizontal displacement covered by this body. Extra is this horizontal displacement, that is nothing but a range, and we know the horizontal distance between the 2 points where they hit the ground, this distance and this distance is same, in fact, because this displacement is equal to this displacement. Extra is, this range, and that is u square sine 2 theta by g. That's the distance between the two stones where they hit the ground. Now one more question we frame over here. What is the distance between the two stones when they are in motion at time t seconds after projection? Distance between the two stones, or separation between the two stones, t seconds after projection. Again simple, this is theta, this is theta, this is u, and even this is u. We know very well, horizontal components are equal, u cos theta and u cos theta. So horizontally they are moving with equal velocity, there will be no horizontal separation between the two. Alright, t second later, as long as both are in motion. Coming to vertical separation, which we need to consider. Okay, this body is going like this, suppose this body is going like this. So this vertical separation we need, this vertical separation. Alright, horizontally both have same velocity. So horizontally they are traveling same displacement, as long as both are in motion. So vertically separation, we know, we need to compute. Here we got that relative velocity is 2u, u and u into time. That was relative separation. Over here it is u sin theta and u sin theta downward. So relative velocity between the two is 2u sin theta. So 2u sin theta into t is the relative separation between the two, or vertical separation between the two. In fact, there will be no horizontal separation as long as both are in motion. Fine. Now we'll try to show if different projectiles are thrown at different angles with different velocities, as long as their max height is same, time of flight will be same. Because time of flight depends only on the vertical part of the projectile motion. So if vertical part of the motion is same, time of flight is going to be same. Let's just check it out or prove it. Suppose this body is projected up with speed u, 1. Another projected at an angle theta with speed u2, fine. Now let us assume the time of flight to be same, and then let's prove that their max height also will be same. Max height is going to be same, right? Time of flight for this body is going to be 2u1 by g. For the other body, it is 2u2 sin theta by g, 2 times vertical component by g, right? If time of flight is given to be equal, then we know u1 is equal to u2 sin theta. Now ratio of max heights we'll try to get. Over here, max height is u1 square by 2g. And here, max height is going to be, instead of u1, instead of u2, we will be writing u2 sin theta, vertical component, because height depends only on vertical motion. So it's going to be u2 squared sin square theta, u2 sin theta squared, by 2g. That's max height in this case for a projectile. We already know the formula for max height. Alright. Now, okay, this 2g can cancel out. We know u1 is equal to u2 sin theta. So u1 squared is u2 sin theta squared. So they are equal in fact. So this you can cancel out, and ratio is 1:1. So when t flight is same, max height is same, or max height is same, t flight is same, irrespective of angle of projection, irrespective of speed of projection, fine. So we know for a vertically projected body, if the height reaches h, max height, then time of ascent will be root 2 h by g, time of descent also will be root 2 h by g, and t flight is going to be twice this, fine. This formula for t flight is valid for a body projected at any angle, any speed, as long as h is max height. Even if this is max height, same formula for this projectile for time of flight. Over here also, if h max height is same, t flight is going to be this. Okay, if t flight is if t flight is given as t, then h is written as 1 by 8 gt square, fine, where t is t flight in fact. From here, you square it, you will get it. And if only time of ascent or time of descent is given, then you can write down h as half gt square. Over here you will get root 2h by g. But then here it is 2 times root 2h by g. Square it, you will get this particular thing if you are using t flight. Alright. Okay. So we know very well. Forget about the half motion of a projectile. Consider later half motion. Okay. Over here velocity is u cos theta. If it is projected with u at an angle theta to the horizontal. Okay. Now we know from the topmost point onwards, it's like a horizontally projected body, and we know very well for a horizontally projected body, vertical part of the motion like a drop body, and time of fall is going to be root 2h by g. All right, and this time will be another equal, so it is going to be 2 times root 2h by g for the whole projectile. Is that clear? Which is also valid for a body project vertically upwards. Next problem: 2 stones are projected horizontally from the top of a tower of height 80 meter in mutually perpendicular direction with velocities 5 and 12 meter per second. What the distance between the 2 stones where they hit the ground? It's pretty simple and interesting question. We know very well in vectors, we have studied, if mod a plus b equal to mod a minus b, then angle between a and b is going to be 90 degrees. That means when vectors a and b are mutually perpendicular, their resultant's magnitude and the difference of the 2 vectors, in fact if you take minus b over here, this is a minus b is this vector. Both will have the same magnitude, and that is going to be root over a squared plus b squared. Fine. So somehow, angle is 90 degree, root over a squared plus b squared plus 2ab cos 90. 2ab cos 90 is 0. So result is going to be this. Whether it is plus 2ab cos theta or minus 2ab cos theta, that need not be considered, should not be considered. So this is going with the magnitude. Now we know velocity of body A relative to b is va minus vb, and its magnitude is going to be root over va squared plus vb squared if they are mutually perpendicular. I mean, resultant will be 13 and even difference also will be 13. Relative velocity is difference of 2 velocities, even that is going to be 13 in this particular case. Fine. Okay, so relative velocity is 13, 5 and 12, resultant 13, difference also 13 because A and B are mutually perpendicular, mod A plus B is mod A minus B. Relative velocity is 13 and both the bodies have the same acceleration g, so relative acceleration is 0, relative velocity 13 will remain constant, and we know both are horizontally projected bodies. For a horizontal projectile, time of fall is just like the time of fall for a drop body, that is root 2h by g, and that you will end up getting as 4 seconds in this case. Okay, so g I'm taking 10, so both the stones hit the ground in 4 seconds. And separation is relative velocity, relative separation we need into time, and that's going to be 52 meters. That's all. We just take relative velocity and time, that's all. Nothing else, because relative acceleration is 0. We need relative separation between the 2 stones where they hit the ground. Next problem. Ship is given with the velocity v1. A bullet is fired vertically with the velocity v2 relative to the ship. What is the range of the bullet as seen by the person on the ground? Okay, we know relative to the ship, it's moving in a vertical direction. That means bullet is going like this, suppose. Now, if bullet is here, ship is here. If bullet is here, ship is here. If bullet is here, ship is here. Finally, bullet will end up in the ship. Fine. Because relative to ship is moving vertically. Forget about all that. We know very well. Time of flight only depends on vertical part of the motion. So time of flight depends only on v2. Okay. So time of flight, just like 2u by g for a vertically projected body, time of flight is 2v2 by g. And this velocity is v1. Horizontal velocity, that remains constant. So time of flight into horizontal velocity is the horizontal distance covered, and that's the range as seen by somebody on the ground. Over. Next problem. A man can throw a stone to a maximum height h. To what maximum distance can he throw? Some of the students who remember the case something like this, 4h equal to r tan theta. Alright. So maximum height h, maximum horizontal distance he can throw, might tell 4h. We know very well when a body is thrown at an angle of 45 degrees with some speed, then range is maximum, and that time range is u square by g, sin 2 theta being 1. At that time this max height is going to be this much. Fine. But that is not the solution here. Definitely here height is h means range is 4h. But that is a single throw. Here it's very clearly mentioned a man can throw a stone to a max height h. What max distance he can throw? That means they are separate throws. So, max height we know is given as h, which is u square by 2g. For max height he need to throw vertically with speed u. With the same speed now, to throw maximum distance he need to throw at 45 degree. At that time max distance will be u square by g, sin 2 theta being 1. Alright, so we need this value u square by g, which is 2h. So this is 2h and not 4h. Okay, a man can throw to max height, a man can throw to max distance. Separate throws, so you need to consider them separately. Instead of this, if the question comes like this, a man throws a stone such that it reaches a maximum distance or, r, what max height it goes, that is a single throw. In that case, this max height should be r by 4 and not r by 2 because it's the same throw. Is that clear? It's very clearly mentioned here. A man can throw a stone to a maximum horizontal distance r. To what max height can he throw? This is r, sorry. This h should be r by 4. Fine. What max height it reaches, that will be r by 4. Clear? You can easily get the relation between height and range for a projectile as 4h equal to r delta, or it could be like this, 4h tan theta equal to r. Suppose even I don't know what is correct. Let's check it out which is correct one. How to not to forget the correct formula. Simple. What we do is, we just project a body at 90 degree to the horizontal with speed u. We know in that case range should become 0. Range should become 0. Fine. It should go up and come back. And now that happens where? Let's see here. Okay, so this formula says r equal to 4h by tan theta. And we know tan 90 is infinite and range becomes 0. So this should be the correct formula. Fine. 4h equal to r tan theta is correct. The relationship between max height and range of a projectile. Of course, for 45 degree, the ratio is 4:1. Fine. This is incorrect. Now we can safely see that. Because in this case, we get 4h equal to r by tan theta. Fine. In this case, it says when theta is 90 degree, height itself is 0 because tan 90 is infinite. But height won't be 0 for 90 degree to the horizontal. It will be range that is 0. So this is the correct formula. 4h equal to r tan theta, relationship between height and range. How to remember the formula like this? You need to remember a formula like this. Don't just by heart without having a concept to get at the right case when you forget them. Next problem. Equations of motion for a projectile are given like this. Okay, we need to find initial velocity, angle of projection, acceleration, maximum height and time flight. Okay, we know this is like u cos theta into t, horizontal motion. Velocity is constant. This is u cos theta, horizontal component which is 5. And vertical component, this is, vertical height, ut sin theta minus half g t squared, right? This is u sin theta. So, vertical component is 12, horizontal component is 5. So obviously initial velocity is going to be 13, 5, 12, 13 triplet. So 13 meter per second. Alright. Now, coming to angle of projection. It's very clear from here. This is 5, this is 12. So if this is theta, so angle of projection is tan theta is 12 by 5 means theta is tan inverse 12 by 5. Fine. At this particular angle, the body is projected. Okay, now. Alright. So this is over. Coming to acceleration. This is half g. Alright. Half g is 5 means g is going to be 10 meter per second square. Minus sign indicates this is downward. Fine. Taking upward direction positive. Because this u sin theta is 12 which is upward, we have taken it positive. Fine. Coming to max height. We know max height depends only on vertical motion. For a vertically projected body, max height is u square by 2g. Over here, vertical velocity square by 2g. That's going to be 12 into 12 by 2g. Right? So this 10, if you cancel out here, it becomes 1.2 and this 2 will, 6 into 1.2, 7.2 meters. That's the maximum height reached by this body. Coming to T-flight. T-flight again depends on vertical part of the motion. We know 2 times vertical velocity by g for a vertically projected body. Over here, vertical velocity is 12. Okay, that is u sin theta, 2 u sin theta by g, or 2 times 12 by g. G is 10 here. So this is going to become 2 into 1.2. Fine. And that's going to be 2.4 seconds T-flight. Fine. Next problem. 2 bodies are projected with 10 meter per second each in opposite direction from a given point. Okay, sufficient height is there. So at what time their velocities will be perpendicular to each other, velocity vectors. We know velocity of a body will be u plus at. In this case acceleration is g. So u is u in this direction and a will, gt will be in the direction of g. This is u and this is gt. Something like this, u plus gt. Alright, this whole thing I am taking as u. Same thing for this body, u, but gt will be in the direction of g. Fine. So this is u, this is gt. So velocity v is u plus gt, tail head resultant, head tail, this is the velocity, t second later. Fine, same thing for this body. It's given these two bodies, the velocity should be mutually perpendicular. This is 90 degree, when this is 45 degree, when this should be 45 degree, when this is 45 degree, when this should be 45 degree. When these two angles are equal, these two sides will be same. So this is 10, so this also should be 10. So 10 equal to gt, so t will be 1 second. So 1 second later, their velocities will be perpendicular to each other, right? In the same problem, what is going to be the separation between the two bodies when velocities are perpendicular to each other? We already got velocities are perpendicular to each other at 1 second. Separation between the two. Alright, we know the velocities 10, 10 are in opposite direction, so relative velocity 10 minus of minus 10, 20, and that relative velocity will remain constant because relative acceleration is 0, both have the same acceleration g, relative acceleration is 0, relative velocity into time, that's going to be the separation, relative separation 20 meters between the two, clear? So that's the answer, 20 meters. Next problem, two bodies are projected with equal speed u, say 10 meters per second, in opposite direction, in horizontal direction. After what time the position vector with respect to point of projection becomes mutually perpendicular to each other? Alright, position vector or displacement vector ut plus half gt square. Ut will be in the direction of u and half gt square will be in the direction of g. Fine, so this will be ut for this body and this will be half gt square for this body, and ut plus half gt square, tail it, this is going to be the displacement r1. For the other body this is ut, this is half gt square, alright. So ut plus half gt square, tail it, this is the displacement r2. These two should be perpendicular, means this 45 degree, this should be 45 degree, means even this should be 45 degree. Okay, two angles equal, two sides equal, ut should be half gt square. Equate them, velocity is given 10, ut equal to half gt squared, and solve it, you will get t equal to 2 seconds. So at that time, what is the separation between the two? Obviously separation is going to be horizontal because vertical motion is similar and we don't feel similarities, we feel only differences. Horizontal motion is different, so it's felt, fine. So separation between the two, when position vectors become perpendicular to each other, is relative velocity, 10 minus of minus 10 is 20, relative velocity into time is 2 seconds, so this is 40 meters obviously. Okay, relative velocity remains constant because acceleration is g for both, so relative acceleration is 0, relative velocity which is 20 remains constant, so constant velocity into time, relative separation between the two. Alright. Next, in this case, what is the time taken for the velocity vectors to be at 120 degree with each other? Okay, once again the same thing, 20 root 3 in opposite direction. V equal to u plus gt. Alright, u plus gt, this is gt. So tail it, head tail, this is the velocity. U plus gt, this is the velocity. These two should be at 120, means this should be 60 degree, this should be 30 degree. Alright, and we know tan 30 is this by this is 1 by root 3. We know tan 30 is gt, I am taking g as 10, gt by 20 root 3. Alright. So this root 3 cancels out and this cancels out. We get t as 2 seconds. Is it clear? So 2 seconds later their velocities will be at 120 degree with each other. At that time, what is the separation between the two bodies? Relative separation. Once again, relative velocity 20 root 3 minus of minus 20 root 3 is 40 root 3. Relative velocity will remain constant. Into time is 2 seconds. That's going to be 80 root 3 meters when their position vectors are at 120 degree with each other. Clear? In the same problem, what's the time after which their position vectors with respect to point of projection become at 120 degree with each other? Okay, but now this is going to be ut and not u, ut, and this will be half gt square because position vector is ut plus half gt square. Alright, ut will be in the direction of u, half gt square in the direction of g, fine. So this is tail it, ut plus half gt square, ut plus half gt square, this is 120 means this is 60 means this is 30 as usual. Tan 30 once again 1 by root 3 equal to this by this is half gt squared by this which is ut, that is 20 root 3 t. So 1 t you can safely cancel out, and okay, root 3 you can cancel out, you get t equal to 4 seconds. In fact this 4, so t equal to 4 seconds. And at that time when their position vectors are at 120 degree with each other, what is the relative separation between the two? Relative separation, relative velocity once again 20 root 3 this side, 20 root 3 this side, 40 root 3, right? Okay, into time is what? 4 seconds, into 4, that's going to be 160 root 3 meters, relative separation between the two bodies. In fact, they are moving horizontally relative to each other because vertical motion is similar, that is not felt. Fine. So many meters when their position vectors are at 120 degree with each other. Clear? Let us now do it as a general problem. Suppose two bodies are projected from a sufficient height from a given point in horizontal direction velocities u1 and u2. After what time their velocities will become perpendicular to each other? Okay, so it's simple. Let's take this direction as x-axis, this upward direction as y-axis. So velocity of the first body will be, okay, u1i minus gtj. Alright, because g is in this direction, so that's the reason I'm taking minus j. Fine. For the other body, velocity v2 at time t, this u2 itself is in minus I direction, so it will be minus u2i minus gtj. Somehow acceleration is same. So now velocity should be perpendicular, means the dot product should be 0. So here it should be 0, and this is going to be ii and jj, means ii is 1. So this is going to become minus u1 u2, and here it's going to be g square t square. Fine. So alright, minus minus it becomes plus. In fact, to bring this side you have u1 u2, okay, by g squared as t squared, and this is going to be t root u1 u2 by g. This is the time after which their velocities become perpendicular to each other, and separation at that time when velocities become perpendicular to each other, relative velocity u1 minus of minus u2 is u1 plus u2, relative velocity remains constant because relative acceleration is 0 into time we have already obtained, so root u1 u2 by g. This will be the separation between the two, okay, when their velocities become perpendicular to each other. This is the time, this is the separation, fine. In the same problem, after what time their position vectors become perpendicular to each other? Alright, so for position vectors, let me write r1 and r2. And r1 will be u1t minus half gt square j. I mean u1t I minus half gt square j. For the other body, u2t, minus u2t I and minus half gt square. Same thing. Now their dot product should be 0. r1 dot r2, their position vectors, this should be perpendicular, means dot product is 0. Now this is what? So, okay, I and j we need to dot. So this is like, minus u1 u2. And t will become t square, and this is minus minus plus, half will become 1/4 g square and t power 4. Fine. So when you simplify this, alright, so t square anyway you can cancel out from here itself, take out common and cancel out. Here t square will remain. The other side you have u1 u2. Okay, now this 4 will go that side. 4 u1 u2 by g square is t square. So after taking root you will end up getting this. Fine. 2 times this. And at that time what the separation between the two bodies? I mean when their position vectors are mutually perpendicular to each other. That will be obviously relative velocity into time. Relative velocity once again u1 minus of minus u2 is u1 plus u2 into time, just this much. That means double of this, so just multiply by 2. This will be separation when their position vectors are perpendicular to each other, right? Consider a case where a body is projected vertically up with initial velocity u. We know its height is given by ut minus half gt square. Okay, taking upward direction positive. Now, okay, it is a quadratic equation in t. That means we get two different values of time for a given height. Okay, one say is t1 and the other is t2. That means while going up, t equals 0 here. While going up, it is at a particular height from 0 to t1, and then this will be t2. Fine. Okay, so a particle will be at a given height at two different times after projection. Okay, so one we are calling it t1, and the other the whole thing right from beginning. This is t2, this is t1. But we know very well. Okay. Time taken to go from here till here will be same as the time taken to come from here till here. So if this is t1, this also is t1, and this whole thing is t2. Sum of these two times will be t flight. Fine. So this is t2 and this is t1, means this is t1. So t1 plus t2 is t flight. So okay. So when you solve this quadratic, you get two different values of time, and sum of those two times will be time of flight. Fine. And in case initial velocity is asked, it's very clearly mentioned, suppose a particle is at a given point in its path at two different times t1 and t2, find t flight. So we know very well t1 plus t2 will be t flight, which is 2u by g. So initial velocity is going to be g into t1 plus t2 by 2. Fine. This is going to be the initial velocity. Clear? Let us take a numerical example. For example, if we project a body vertically upward with a velocity of say 49 meters per second, that is 5g, every second body will lose a velocity equal to g. So it's going to reach here in 5 seconds. So at t equal to 5, it will be here at the top, right? So somewhere here, suppose at t equal to 1, okay, 2, 3, 4 and 5. Alright, so here, okay, distance got in the last second while going up, distance got in the first second while coming down, g by 2, fine. So here it will be at 6 seconds, 7, 8, 9 and back 10. Here t is 0. See, t flight 2u by g, 2 into 49 by 9.8. Alright, this is 5 into 2, 10 seconds. T flight is 10 seconds. 5 seconds to go up and 5 seconds to come back. Alright, see, 0 plus 10, 10. 1 plus 9, 10. 2 plus 8, 10. 3 plus 7, 10. 4 plus 6, 10. 5 plus 5, 10. Fine. So, at a given point, while going up and coming down, body will be at two different time instants. Some of those times will give you t flight. Clear? This is valid not only for a vertically projected body, but also for a projectile. But in case of a vertically projected body, we can safely say it will be at a given point. In case of projectile, we can't say at a given point. We can safely say at a given height. Fine. Say, this is point P. This is time t1. Okay. And this is time t2. If this is t1, even this will be t2, same height, fine. This is t1, this will be t1, and this is t2, fine. So, from beginning, 0 to t1, 0 to t2, t2 plus t1 will be t flight, fine. At t1 and t2 bodies at the same height. Sum of those two times will be t flight, clear? Suppose a body is projected with 30 meters per second. What is the maximum height reached by the body? We can either go by u square by 2g, which is a basic formula for max height. Okay, so we'll end up getting like 15 into 345 meters. Otherwise, whenever a body is projected upward with a certain velocity, in first second it will cover u minus g by 2, means 30 minus 5. Alright, so in first second 25, and subsequently g less, okay, so last second 5, so 3 seconds, we know already its velocity is 3g, so it will be lost in 3 seconds, every second it loses 10, so in 3 seconds we will reach the top. Okay, first second u minus g by 2, then difference should be g, 3 seconds over, so 20 plus 25, 45 meters. Alright, valid even for a projectile, but vertical part of the projectile motion, fine. Suppose a body is dropped from certain height, okay, and it reaches the ground in 4 seconds. What is the height of fall? Either you can get by half gt square as 80 meters, or you can even go like this. First second 5 meters, g by 2, starting from rest. Next second 15, difference should be g, okay, this is 60 plus 20, 80 meters. Next problem, 4 seconds after projection at an angle theta, a particle is at point P. 5 more seconds later, it hits the ground. Height of point P is, take g as 10 meter per second square. Okay, we know this is 4 seconds and this is 5 seconds, so T flight is going to be 9 seconds, so time to go up 4.5, come back 4.5, fine. So time depends only on vertical component. We know very well, in 4.5 seconds vertical component of velocity is becoming 0, means initially vertical component of velocity should be 4.5 g meter per second, fine. Now, okay, it reaches this point P in 4 seconds. Whenever vertical component of velocity is u, in first second body travels while going up minus g by 2, means 40 meters. Next second, difference should be g, and difference should be g. In 4 seconds it's a drop. Sorry, this should be 10. Alright, so 30 plus 30, 60 plus 100 meters. So height of that point is 100 meters from the ground. Otherwise also, we can straight away go in a simple systematic way. We know T flight of a projectile. 4 plus 5 is going to be 9 seconds, and that 9 will be 2u sine theta by g. From that, you get u sine theta, which is vertical component. Fine. Once you know the vertical component of velocity, you can get height as ut sine theta minus half gt square. Just plug in the value of t as 4 seconds and u sine theta is already known from here. You will get that. Fine. Next problem. Two particles moving towards each other with velocities u1 and u2, okay, have deceleration a1 and a2. What is the minimum separation for these particles to not to collide? We can do this in relative motion. So relative velocity in initially is u1 minus of minus u2 is going to be u1 plus u2, and relative acceleration, okay, is going to be acceleration of a minus acceleration of b. Okay, minus of minus means is going to be this much, but of course it is deceleration. Relative deceleration I should say, or relative acceleration is minus of this. Alright, okay, what is the separation required? Until final relative velocity becomes 0. For them to not to collide, relative velocity should become 0. Remember, individual velocities need not be 0. Relative velocity should become 0 before the separation becomes 0, or just before their collision. So u, v, a, yes, this type of equation we need. So, okay, just like in case of vertically projected body, we take velocity becomes 0, height reached, u square by 2g, like that here. Instead of you will be using relative velocity by 2a, for a I'll be writing a1 plus a2, relative deceleration. This is a minimum separation for them to not to collide. Fine. Next problem. Here it is given balloon is moving up with an acceleration of 15.7 meter per second square. A stone is dropped from it. 4 seconds later, another stone is dropped from it. Separation between the two stones 6 seconds after the second stone is dropped. Okay, fine. So initially stone is dropped from it. Its acceleration is this much. Okay, so what's happening? Suppose the velocity of the balloon is u, even velocity of the stone will be u. Of course, the moment you drop it, acceleration of the stone will become g, 9.8 meter per second square downward, and acceleration of the balloon is this. But initially velocity of the balloon and the stone will be same, means relative initial velocity is 0. So let's do this problem in a relative way. Relative initial velocity is 0, relative acceleration. We know these two accelerations are in opposite direction. Acceleration of the stone relative to balloon, g minus of minus this is going to be, this plus this is going to be 25.5 meter per second square. Relative acceleration. Okay, time 4 seconds. When the second stone is just dropped, okay, till that time, how much relative separation happens between this balloon and this first stone? Of course, second stone is still in the balloon. Alright. Now, this is going to be half a t square. Relative separation between balloon and the first stone. Half a is 25.5 into t squared is 16. Alright, so this is going to be 8 into this. Okay, 204 meters. So first stone and balloon will be 204 meters apart when the second stone is just dropped. But by the time stone will have what velocity related to the balloon? Okay, velocity is required related to balloon. Final relative velocity means at t equal to 4. Okay, we know this condition. Relative to balloon, stone is having an acceleration of 25.5. So velocity v equal to 80 in 4 seconds. Initial velocity 0 related to balloon for the first stone. 80, acceleration is 25.5, time 4 seconds. So this velocity is going to be 102 meter per second. Right. So this is the velocity of the first stone when the second stone is dropped. Relative velocity, I mean velocity of the first stone relative to the second stone. Alright, so now we need separation between the two stones, 6 more seconds later. Okay, now we can proceed further like this. Velocity of the first stone relative to the second stone, 102 meter per second. Okay, now both the stones have same acceleration because both are in free motion now, g. Okay, now we want separation between the stones now. So both the stones are freely moving under gravity, so relative acceleration 0 now. So relative separation in another 6 seconds will be, just relative velocity into time. Relative velocity between the two stones, we already got that. 102 into time is 6 seconds. This is going to be 612, I think 612 meter per second. Fine. Sorry, not meter per second, it's just meters, so many meters. That is the increase in separation of the stones in next 6 seconds. Earlier they are already 204 meter apart. Another 612 you need to add. So altogether 816 meter apart. 6 seconds after the second stone is dropped. Next problem, it's given balloon is moving up with an acceleration of 15.7 meter per second square. A stone is dropped from it. 4 seconds later, another stone is dropped from it. Separation between the two stones 6 seconds after the second stone is dropped. Fine. Okay, the moment you drop the stone, initially the stone will have the same initial velocity as the balloon. Second stone is still inside the balloon. Fine. But the acceleration of the stone will be now g downward. Acceleration of the balloon is 15.7 upward. So relative initial velocity 0. Relative acceleration, they are in opposite direction. So minus of minus, that's going to be this plus this is going to be 25.5 meter per second square. Alright. Okay. This is 0.2 less, so I'm just subtracting 0.1, making it 10 plus 15.5, something like that. Fine. And what about relative separation in 4 seconds, right? Use the equation s equal to ut plus half it square. Just use the relative velocity 0 initially. So relative separation between the balloon and the first stone or second stone and the first stone at 4 seconds will be half a t squared. T squared is 16, 4 squared, fine. So this is 8 into this. This is going to be, alright, 25 into 8, 200, 0.5 into 8, 4. So 204 meters, right? Now second stone is dropped. 1 second stone is dropped. Even that will have the same acceleration. Relative acceleration 0. And what about relative velocity? See, with respect to the second stone, first stone has moved with a relative acceleration of so much for 4 seconds. So we need relative velocity, suppose. Then that relative velocity at t equal to 4. Alright. So relative velocity at t equal to 4. That becomes initial relative velocity when the two stones are moving freely. That will be 80, and a is 25.5 into t is 4, so this is going to be 102 meter per second. With this velocity, they will move for next 6 seconds with constant velocity, mind you, because there is no relative acceleration once both the stones are moving freely under gravity. With this constant velocity, they are moving for 6 seconds, so this separation is another 612 meters. 612 plus earlier separation between the two stones, 204, that's going to be 816 meters. Clear? Next problem, it's given a block slides down a smooth incline of base length 9.8 meter. Okay, we need to find the value of theta for the time to be minimum. Okay, we know very well, if this length, hypotenuse is L and this is theta, this will be L cos theta. But if this is L, then this will be L by cos theta. So it's starting from rest and moving with a constant acceleration g sin theta down the incline. We know for a dropped body, time will be root 2 h by g like. Same way here, time to come down will be root 2. For h we will be writing this length which is L by cos theta. So L by cos theta, taking base length as L which is constant. Alright, so now by g, but for g I'll be writing g sin theta because here acceleration is g sin theta. Fine, so this is g sin theta. So we want this time to be least. Alright, base length is fixed, g is fixed. Alright, what we do is we multiply here by 2 and divide by 2. Alright, so in the denominator we have whatever is the numerator, doesn't matter. Denominator you have 2 sin theta cos theta, which, okay, let it be x, and here I can write down sin 2 theta into g. Fine. This is constant, this is constant. Alright, instead of writing x, let me write it k because normally x means variable. we used to denote x variables. Fine. Sine 2 theta denominator should be maximum for time to be least, and sine 2 theta's max value is 1 when sine 90, so 2 theta should be 90 degree, means theta should be 45 degree. So at 45 degree, okay, for a given base length, if this theta is 45 degree, time of sliding will be least on a smooth incline. Fine. Next question, if the man stands here, a moving escalator takes him up in 1 minute, and if the escalator is not moving and the man walks up, he takes 3 minutes to reach the top. If the man walks up a moving escalator, how much time he takes to reach the top? Alright, so suppose escalator is moving with the velocity v1, then 1 minute time t1, which is given as 1 minute, will be distance by velocity L by v1. Now t2, when the man alone walks, escalator is not moving, when the man walks up, then it carries up, he moves up in t2 3 minutes, L by v2. Velocity of man related to escalator, I am taking v2. Okay, now when man is walking up a moving escalator, he will be moving at the velocity v1 plus v2. Both velocities will be there in the same direction, will add up. So time will be now L by v1 plus v2. Fine. L by v1 plus v2. In fact, something like this. Now this is L. What about v1? From here we can easily get v1 is L by t1. Fine. So let me write down here L by t1, and here v2 will be L by t2. Alright. So L I can take out common. In fact, if I take L common and cancel out, I get 1 by t1 plus 1 by t2. Alright. This take LCM in the denominator, you get t1 t2 goes in the numerator, and here you will have t1 plus t2. So this is going to be t1 t2 by t1 plus t2. Fine. And over here we have 1 minute and 3 minutes. So this is 3 times, so answer will be 3 by 4. Alright. So many minutes or 45 seconds. Is that clear? One thing I want to tell here, whenever you come across something like t1 t2 by t1 plus t2 type of term, in when resistors are in parallel, you get something like R1 R2 by R1 plus R2. Okay, or when capacitors are in series, alright, you will get something like C1 C2 by C1 plus C2. Okay, and even when you are determining the focal length of a lens or a mirror, UV by U plus V, whenever you get a term something like product by some like, wherever it is, it could be at many other places, you can use a simple shortcut. Here, we know T1 was 1 minute and it was given T2 was 3 minutes. So I needed T1 T2 by T1 plus T2. Alright, so the bigger term is how many times smaller term? 3 times. So take bigger term and divide by 1 number extra. So it's thrice means divide by 4. This is the answer. So many minutes. Okay, here let me show it. For example, when two resistors 10 ohm and 40 ohm are in parallel, what is the effective resistance? You can easily do it by R1 R2 by R1 plus R2. Okay, but then this is how many times? 4 times. So divide by 5. 1 number extra. So 40 by 5. That's going to be 8 ohm. Okay. Suppose it's given an object placed 20 centimeter on one side of a lens forms an image 30 centimeter on the other side. Alright. So obviously lens is forming image on the other side means it will be real image. So it's going to be UV by U plus V focal length. We need focal length suppose. This is how many times? Okay, 20, 30. 30 is 1.5 times. So bigger number divide by 1 number extra. 1.5 plus 1, 2.5. So this is going to be the answer. So now into 4, right? This becomes 10 and then 1 0 cancels, 3 into 4, 12 centimeter. That becomes the focal length. Clear? Next question. Can a body have zero velocity and still be accelerating? I mean zero velocity and non-zero acceleration. Obviously, yes. When you project a body vertically upward, at the topmost point, velocity is 0, but acceleration is not 0 because force is there. Okay, so you can write F equal to ma and then you will get acceleration as g, even though its instantaneous velocity is 0. Fine. Another example you can have, simple harmonic motion at the extreme position. We know its velocity becomes 0, but acceleration is maximum in fact. And here we have a case where velocity is 0, but acceleration is not 0. Fine. Is the converse true where velocity is not 0 and acceleration is 0? Obviously true when the body is moving with a uniform velocity. Velocity is not 0, acceleration is 0. Fine. Next question. Can a body have increasing velocity and decreasing acceleration? Can it have decreasing velocity and increasing acceleration? Obviously. Let's check out the first thing. Increasing velocity, decreasing acceleration. Okay, when the body is starting from rest, from extreme position in simple harmonic motion, as it is moving towards equilibrium, we know its velocity increases because velocity is maximum at equilibrium position. Fine. So here velocity is 0. So velocity is increasing, but acceleration is decreasing. Here acceleration is maximum, here acceleration becomes 0. Fine. So we definitely have a case where velocity is increasing and acceleration is decreasing. Fine. Now let us proceed further. So as the body is moving from equilibrium towards extreme, here velocity is becoming 0. Here maximum. Right. So velocity is decreasing and acceleration is increasing. So decreasing velocity, increasing acceleration is also possible for the other half. of the motion, okay, when a particle is moving from one extreme to the other extreme. Is that clear? Next question. When a vehicle is accelerating, does it mean it's speeding up or slowing down? Obviously not. Because even with constant speed, vehicle can accelerate. You can just turn the steering wheel, fine. It's not that you need to press the accelerator to accelerate the vehicle. You can even use the steering wheel to accelerate. Fine. Turning also changes the velocity. Direction is changing, velocity is changing, body is accelerating. You don't need to increase your petrol input to accelerate. You can even, use the steering wheel without increasing the petrol input. You can accelerate the vehicle. Fine. Next problem. It's given car accelerates from rest with an acceleration alpha and then decelerates at the rate beta, finally comes to rest. Total time of travel is t. Find the maximum velocity of the car and also the displacement. Pretty simple. Okay, total time is given t. Let this time be t1 and let this time be t2. Okay. And here, let Vmax be the maximum velocity. We need to compute that. We know for this equation, V equal to U plus AT means alpha t1. Alright. And for this part of the journey, same V, we can write on beta t2. Okay, decelerating at beta to come to rest. You can imagine the other way. You can imagine it's accelerating from 0 to Vmax at the rate beta. Just consider the reverse way, doesn't matter. We need to eliminate T1 and T2 because total time is known. So this equation we need to multiply by beta and this equation by alpha. Now you can add this up. So alpha beta is common, T1 plus T2 will become T, and here V is common and you have alpha plus beta. Finally we need this V. So V equal to alpha beta by alpha plus beta into T. Alright. Okay. And here this Vmax we already got. Fine. Average velocity for the first half of the journey 0 plus Vmax by 2 is V by 2. For the second half of the journey V plus 0 by 2 V by 2. For the entire journey average velocity will be V by 2 only. Fine. First half V by 2, second half V by 2. For the whole journey it is V by 2. For example, first 15 days you are eating 5 rotis a day, 5 chapatis a day. Next 15 days you are eating 5 chapatis a day. The whole month you are eating 5 chapatis a day on an average. Fine. Same thing. Now, what is the total displacement? Total displacement will be average velocity into time. Fine. Average velocity will be, this V by 2, half of this. Okay, half of this, alpha beta by alpha plus beta into T. This is average velocity. Into time I need, so another time. So this is something like this. So, if you notice carefully, okay, it's something like when a body is starting from rest with this particular acceleration, alpha beta by alpha plus beta, at the end of time t, it will have this particular velocity, at like. Similarly, half at square like. So instead of acceleration, we are using alpha beta by alpha plus beta. Okay, where acceleration is alpha, deceleration is beta. Okay, in between there is no uniform velocity, just accelerating and then just decelerating. In fact, this is the situation where the car will be covering the distance between A to B, if I call A and B, in least time. Just go on accelerating, whatever maximum acceleration engines can give, and go on apply brake and get the deceleration, that's all. Accelerate and decelerate. No uniform velocity. So minimum time in which car can cover is asked, means you can use this concepts. Fine. Same approach. But for acceleration, to solve problems, we can definitely use alpha beta by alpha plus beta. But if specifically acceleration for the whole journey is asked, average acceleration for the whole journey, it's not alpha beta by alpha plus beta. It is 0 because initial velocity is 0, final velocity is 0. Total change in velocity by total time is average acceleration. That is obviously 0 for the journey. For the sake of solving problems, you can use this. But if average acceleration is specifically asked, that's 0. Fine. Let's do one numerical here. Suppose engines of a car can give it an acceleration of 1 meter per second square and brakes can give it a deceleration of 3 meter per second square. What is the minimum time in which car can travel a displacement of 384 meter in a straight line? Fine. Starting from rest to rest. Fine. So, okay. So, just like for a drop body, what we do? Time will be root 2h by g. Like that. So, here it's going to be root 2s by a. So 384 by a. But for acceleration, while solving problems, you can safely use alpha beta by alpha plus beta like. So 1 into 3 by 1 plus 3. Fine. So 1 into 3 by 1 plus 3 is 4, which I am writing in the numerator. Fine. Okay. So this you can safely divide by 3. 3 ones are 3 here. Alright. And the numerator. Okay. Let me write it here 1. And this, 8. 2 times, and here 2 more 24 means 8 times. 128 into 2 is 256. 256 within root, comes out as 16. And this 4 within root, outside it will be 2. So it's going to be 32 seconds minimum time in which this car will be able to travel this displacement from rest to rest. Let's try to do this problem by a different method. Both the bodies having equal speed when they just collide. Okay, so drop body is equal to velocity v. Okay, in time t. In the same time the body is traveled from here till here and speed is v. We know 0 to v in some displacement. For the other body, if that doesn't collide, it will definitely go from v to 0. That means it will reach the same height in same time, obviously, because time to acquire a velocity from 0 to v with an acceleration g will be same as the time taken to decelerate and acquire a velocity 0 from v to 0, 0 to v, same time. Okay, so v to 0, 0 to v, same time, but that time is also same as the time taken by this body, projected body to go from here till here, because by the time in which first body, drop body comes from here till here, in the same time the body has traveled here, in another equal time it will go there. That means this is half the time and this is half the time. So we know where for a drop body it will be, equal time intervals means starting from rest, moving with uniform acceleration, ratio of displacements will be, 1:3. Next problem, position vector is given like this. We need to find acceleration when velocity becomes 0. Okay, so to get velocity, we need to differentiate the position vector dx by dt. Okay, we are going to use the formula d by dx x power n is nx power n minus 1. Okay, so this will come here and then, power should reduce by 1. Moreover, if there is some constant here, that can safely taken out. That will be out, fine. It remains as it is here, out, fine. So same thing here. Now here, we need to differentiate this. This 3 will come here, 2 is staying as it is, 2 into 3, 6, power should decrease by 1, t square. This 2 into 21, 42, power should decrease by 1, so it should be t. And here it's already 1, so 1 minus 1, 0, but that 1 into 60 will become 60, alright. And t will vanish, t power 0 is 1, and constant's derivative is 0. Okay, d by dt of constant is obviously 0. Constant is not changing with time. This is velocity at time t. We want acceleration when velocity becomes 0. This velocity we need to take it as 0. At that time we need to find acceleration. But let us get the equation of acceleration. Acceleration is basically dv by dt. Differentiate once again this velocity equation. That's going to be 12t. 12t power should decrease by 1, and here just 42. Constant derivative 0. This is acceleration. But we want acceleration when velocity is 0. So this velocity term, we are taking it 0. You can take out 6 common and cancel out, and we can safely write down t square plus 7t plus 10 equal to 0. Okay, this can be written as t square plus 5t plus 2t plus 10 equal to 0. On simplification, you can easily get this. I can take t common, t plus 5, and here I can take on 2 common, t plus 5 is 0. So this is t plus 5 into t plus 2 equal to 0. That means t is either minus 2 or minus 5, at which acceleration is 0. So, velocity is 0. We need acceleration when velocity is 0, and velocity is 0 at 2 times t equal to minus 5 and t equal to minus 2 seconds. Substitute this 2 here. So first let us substitute t equal to minus 2 here. So we get minus 24 plus 42 is going to be 18. And when you substitute minus 5 here, minus 5 into 12 is going to be minus 60 plus 42 is going to be minus 18. Alright, so these are the values of acceleration, so many meter per second square when velocity is 0. Clear? Suppose a projectile is projected horizontally with velocity from the top of a tower. Okay, we know it goes in this parabola. If we try to analyze it in the form like ut plus half gt square, obviously half gt square will be in the direction of g, and ut will be in the direction of ut half gt square. This is the position vector. Tail head tail, sum of these two. Okay, r vector. ut plus half gt square. Tail head tail, this is the position vector. ut plus half gt square. ut in the direction of u. ut plus half gt square. Fine. This is ut and this is half gt square. Fine. Tail head tail. This is the displacement vector. R vector when it hits the ground. Initial position, final position. So, okay, this is the path. Of course, it's not going this way and then coming like this. Effect I am showing. Effect is this. But when I show it independently, ut half gt square, 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 ut half gt square. Locus of these arrows, that is the path. Fine. Same argument we can use for a projectile motion. Suppose a body is projected with a speed u at an angle theta. In the absence of gravity, suppose it will be at point P 3 seconds later. If gravity is present, where the body would have been at t equal to 3 seconds. Obviously, in the absence of gravity, it would have been at point P 3 seconds later. Okay? If gravity were present, where the body will be at 3 seconds. We know, same argument. We know this is going to move in a parabolic path like this. So, okay, its position vector, initial position vector here, origin let me consider. Position vector will be again ut plus half gt square. Ut will be in the direction of u and half gt square in the direction of g. So ut plus half gt square. 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 Okay, ut plus half gt square. 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 That's displacement is range finally. tail head, resultant head tail. Fine, something like that. So it would have been at this point P in the absence of gravity, it would have gone in straight line with uniform velocity. In 3 seconds it will fall down from P by what distance? Half gt square. So this is half gt square. Particle actually is going like this in the presence of gravity. In the absence of gravity, this would have been path ut half gt square. This would have been absent in the absence of gravity, but gravity is present means this term half gt square below P, half gt square below P. That's going to be, it will be 45 meter below P, vertically below P in the presence of gravity 3 seconds later, 3 seconds after projection. Next, pretty interesting question. It's given orbital velocity of a satellite revolving very close to Earth's surface is 8 km per second. Now, what is the maximum distance up to which one can see from the top of a tower of height 80 meter? Okay, see, when we are standing on the top of a tower of height 80 meter, light travels in a straight line like this. So we can see only up to this. Beyond this we can't see because light from this point won't reach there. Fine. So we need this distance. We know in the absence of gravity, a satellite which is projected like this, say with a velocity of 8 km per second, would have traveled straight like this, in just like light. Would have reached you. But because of gravity, it is following the curvature of the Earth. It's moving along the surface of the Earth, very close to Earth, like this. Fine. And, alright. So, in the absence of gravity, it would have just traveled ut. But due to gravity, half gt square, ut, 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 half gt square. So this is the path actually. Tailhead, head tail, tailhead, head tail, tailhead, head tail, tailhead, head tail. So finally it's going like this. So this is half gt square. 80 is half gt square, 80 is half gt squared. So that will give you t as 4 seconds. Once you know t is 4 seconds. So this satellite is traveling with 8 km per second for 4 seconds. So 4 seconds means 8 into 4, 32 kilometers. We can see up to 32 kilometers. Clear? Next problem. It is given a body is projected with a velocity of 58.8 meter per second. This is 6g at 30 degree to the horizontal. At what time it is at this particular height? You know this is 4g. Height is 4g meters. We know vertical component is u sin theta. Okay, sin 30 is half, so this is going to be, 6g is half is going to be 3g meter per second, vertical component of velocity. And we also know when a body is projected up with some velocity u, in first second we will cover u minus g by 2 while going up. If it is thrown down with u, in first second we will cover u plus g by 2. Okay, so u minus g by 2, 3g minus g by 2 is going to be 2.5 g in first second. And in subsequent second it will cover 1.5 g because difference should be g. For a body moving with uniform acceleration, difference should be acceleration. So it's going to cover 4g meters in 2 seconds, first second, second second. So it will be at that particular height, 4g meters in 2 seconds. Moreover, we know it's projected with 3g means in 3 seconds it will be at the top because every second vertical component of velocity will decrease by g. So 3g means 3 seconds to reach the top, 4g means 4 seconds to reach the top, 10g means 10 seconds to reach the top. And we know 3 seconds to reach the top, another 3 to come back. Fine. And we know very well. It is at t equal to 2 seconds at this particular height, suppose 39.2 meters. 3 seconds, 1 more second here to go there and 1 more to come back to the same height. So at 4 seconds as well, the body will be at the same height. So answer should be 2 seconds and 4 seconds. At these two particular intervals of time, at the 2 particular instants of time, body will be at the same height, 39.2. Otherwise also you can use systematic formula in projectile motion. We need this particular height. We know for a vertical part of the motion, ut sin theta minus half gt square. Okay, you get a quadratic, solve it, you will get 2 times 2 and 4. Fine. Next problem. It's given a body is projected at 30 degree to the horizontal with velocity u. Max height is 15. If it were projected vertically, what is going to be the max height? We know very well, here max height is u square by 2g. Alright. And here it's going to be u square sin square theta. Vertical, it depends on the vertical component. U square sin square theta by 2g. Fine. Okay, this is given as 15 meters. This is given as 15 meters. We know very well. This is basically u square sin square theta. This is basically u square by 2g into sin square theta. Sin square 30 is 1 by 4. This is given as 15 meters. Alright, so we need this. 4 into 15, 60 meters. Clear? When you project vertically, h max is going to be 60 meters. Next problem. A body is projected at an angle theta with certain velocity. Maximum height is given h. We need to find time of ascent. We know at the topmost point velocity will be horizontal. If we consider second part of the journey, vertical part of the motion of a horizontal projectile is like a drop body and time of fall will be 2h by g. This is valid for a body projected at any angle, any speed. So time of fall is this, means time of ascent also this much. Fine. So time of ascent is straight away this irrespective angle and initial speed. When h max is there, you know time of fall will be time of ascent or time of descent will be root 2 h by g, and time of flight will be 2 times root 2 h by g, valid for any angle, any speed. Height same, time same, height same. Next problem. A body is projected in an inclined direction. 2 second and 6 second after projection, body is at the same height. Find max height. We know this is 2 seconds, means even this will be 2 seconds. This is 6 and this is 2. Put together 8 seconds becomes t flight. Okay, we already know when a body is at the same height at t1 and t2, sum of those two times will give you t flight. Okay, so here t flight is 8 seconds. So just to come down, it will take 4 seconds. At the topmost point, it's moving horizontally. Now we know very well. Okay, vertical part of the motion is like a drop body. So h equal to half gt square, where t will be t ascent or t descent is valid for a body projected at any angle. Alright, so h max will be straight away half g into t square. Just t descent or t ascent is to be required. 4 seconds, 4 square is going to be 16, and that's going to be 80 meter. This is the thing. Fine. Next problem. Here velocity time graph of a rocket's motion is given, which is launched from the surface of the earth. We need to find the maximum height reached by the rocket. It's a really interesting problem because maximum velocity is not given. We need to find even that. Fine. Okay. So here, starting from rest, initial velocity is 0, and uniformly accelerating, slope of velocity time graph gives acceleration. Slope is constant, straight line. Fine. Here velocity is maximum. Thereafter velocity decreases, means we can safely conclude that at this particular time, that is 30 seconds, fuel gets over. Thereafter it will be decelerating uniformly at the rate of g, which is given as 10 meter per second square. Fine. Now, okay, its velocity becomes 0 in another 60 seconds. 30 to 90 means in 60 seconds velocity becomes 0. But we know very well, when a body is decelerating freely under gravity, every second while going up, it loses a velocity of about 10 meter per second. So in 60 seconds, it will be losing a velocity of 600 meter per second to, okay, and it becomes 0 here. Fine. That means maximum velocity is 600 meter per second. This maximum velocity is 600. Once we know this, area is displacement. Velocity time graph's area will give you displacement or max height reached by this particular rocket. That will be half into base into height for this particular triangle, right? And that is half into height is 300 into base is 90. This is going to be 27000 meters or 27 kilometers. That's the max height reached by this rocket. Fine. Next problem. It's given a body is projected at 45 degrees to the horizontal from a wall which is 30 meter away. It hits the wall at 26.4 meter. We need to find initial velocity. G is given this much. Fine. Straight away we have a relationship between x and y. So the formula which relates these two is this: y equal to x tan theta minus gx square by 2u square cos square theta. That's equation of trajectory of a projectile. Fine. We need this u. Let's plug in the values. Okay, y is given 26.4 meter. Okay, x is 30 meters. Tan 45 is 1, so need not write that. G is given 10. X squared is 900. Alright, because x is 30. By 2u squared cos square theta. Cos square theta is half because cos theta is 1 by root 2. Okay, fine. Now, bring this, all this term this side and this the other side. We end up getting something like this. Okay, 30 minus 26.4 is going to be 3.6, and that is equal to, this is basically, 9,000 by u squared. So we need u. So u is basically 9000 by 3.6 within root. Fine. Alright, u square is this, I'm taking root. So we add one more 0 and multiplying by 10 numerator and denominator. This is 6 and this is 103, 300. 300 by 6. 300 by 6 is 50 meter per second. That's the answer. Fine. Next problem. It's like this. Two trains each of length 100 meter are moving along parallel tracks. When they move in opposite direction, they take 10 seconds to cross each other. When they move in the same direction, they take 20 seconds to cross each other. We need to find the velocities of individual trains. Okay, it's pretty interesting problem. See, suppose velocity of this train relative to this, means velocity of this train as seen by this train, assuming this train at rest. So, relatively how much separation they need to cover to cross each other. So, this much plus this much. So, 200 meters. In fact, it's something like this. See, imagine this palm length is equal to length of each train. This is another train. Alright. See, this train relative to that train will cover how much? 100, another 100. Only then they will be crossing each other, right? 100, another 100. So relative separation to be covered is 200 meters and time 10 seconds. That is, u1 plus u2, when they are moving in opposite direction, relative velocity will numerically add up. u1 minus of minus u2. Say u1 and u2. Together they are covering u1 plus u2 per second. Fine. And when they are moving in same direction, relative separation to be covered is same, but that's happening in 20 seconds. Distance by time is relative velocity in this case, and that is u1 minus u2 when they are moving in the same direction. Fine. So this is basically 20 and this is basically 10. Fine. This is 10. So we have a relationship like this. u1 plus u2 is 20. u1 minus u2 is 10. You can easily compute this. Add up, you get 2 u1 equal to 30. So u1 is 15. And once u1 is 15, the other has to be 5 for sum to be 20. Okay. So we know the velocities of trains are 15 and 5 meter per second. Fine. The other way to do this is just divide this. Okay. So here u1 plus u2, u1 minus u2 is 20 by 10. Okay, don't take the ratio. What's the diff here? Difference. 10. Okay, so that difference you divide into two parts. 5. So now the numerator you can write something like this. That 15 plus diff, 15 minus diff. Fine. Diff was actually 10. We are dividing the diff into two parts and that each part we are writing here. Fine. So now this is u1, this is u2. u1 plus u2, u1 minus u2. This is u1, this is u2. That's what we got. Fine. Let me show it for one more calculation. Suppose a plus b is 17 and a minus b is 3. We can add up and get 2a equal to 20 and a is 10. Put it a as 10, you will get b as 10. 7. That's one way. The other way what I was following was just divide these two. And then what's the diff here? 14. The diff I am dividing into two parts. 14 by 2, 7. And now I can write this as something plus 7. Obviously it should be 10 plus 7. And this should be 10 minus 7. Okay. So this is a, this is b. Fine. A plus b, 10 plus 7, a minus b, 10 minus 7. Clear? So a and b are 10 and 7. That's one way to do it. Fine. Now, suppose you have an equation like this, f by f plus phi equal to 6 by 7. You will come across many such equations when you are doing problems in sound, beats and all. Fine. Okay. Here, how to do it? What's the diff? 1. Difference is 1. Here diff is 5. So, difference 1 corresponds to difference 5. So, 1 is 5. So, 6 will be 30. 6 will be 30. That means f will be 30. Is it clear? 30 hertz frequency if it is. Fine. Over here. Okay, it's given f by f plus 6 is 7 by 8. What is the diff? 1. Diff 6. So 1 diff corresponds to 6 here. Okay, 1 equal to 6. So 7 equal to 7 into 6, that will be 42. So f is 42 hertz in case it is frequency. Fine. Let's discuss few concepts. Suppose if a particle is starting from rest with constant acceleration, then path will be straight line. Definitely straight line. Okay, because we know s equal to ut is 0, half at squared. Displacement will always be in the direction of acceleration, and acceleration is constant means it's in the given direction, in same direction displacement will be present. Fine, even velocity will be in the same direction because we can write v equal to at. So velocity, acceleration, displacement all will be in the same direction. Okay, and path will be definitely a straight line. Whenever a body is starting from rest, moving with uniform acceleration, path will be straight line. Converse need not be true. That means whenever a body is moving in a straight line, its acceleration need not be constant, because even in a straight line you can move with a variable acceleration. You can slow down, run, all the things. Fine. Now, if initial velocity is not 0 but acceleration is constant, initial velocity is not 0 but acceleration is constant, then two cases arise. Path will be either straight line or parabola. Okay. If u is not 0, acceleration is constant, and angle between velocity and acceleration is either 0 degree or 180 degree. That means just consider the example of a vertical motion under gravity. G is down, and if you throw a body vertically upward, angle between u and acceleration is 180 degree. We know very well when we throw the body vertically upward, path is going to be straight line. Or if you throw the body downward, velocity and acceleration both are in the same direction. Now angle between initial velocity and acceleration is 0 degree. In that case also path is going to be straight line. So when angle between velocity, initial velocity and acceleration is either 0 degree or 180 degree, path will be straight line. Mind you, acceleration is constant here. Okay. Of course, a body can move in a straight line with variable acceleration, but that's not the question here. Here very clearly it's mentioned initial velocity is not zero and acceleration is constant, then path will be straight line under these conditions. And otherwise it will be parabola. When angle between initial velocity and acceleration is other than 0 degree and 180 degree, then path will be parabola. Say acceleration is this side, and we are not throwing upward or downward, but throwing any other direction, path will be parabola. Fine. We have already seen a general equation for the trajectory of a projectile as y equal to ax minus bx square. This equation you will get for the path of the projectile or path of a particle which is moving with uniform acceleration, where angle between initial velocity and acceleration is other than 0 and 180 degree. Fine. You get an equation like this, which is the general equation of parabola. So path will be either straight line or parabola. Converse need not be true. I mean, when particle is moving in a straight line or parabola, acceleration need not be constant. Fine. Let us consider a case where a train is moving horizontally with a constant velocity u, okay, on a bridge, and one person is standing on the ground here. The passenger sitting inside the train drops a stone. What will be the path of this stone as in by this person on the ground and as in with the passenger in the train? Let's see. Okay, due to inertia of motion, this stone will have same initial velocity as that of the train. Alright. Now, as seen by this person on the ground, initial velocity is u and acceleration is g down, so path will be parabola like this with an acceleration g down. Fine. But coming to this passenger, we know this train is moving with a constant velocity u. Even this particular ball or this particular stone is also in horizontal direction moving with the same velocity u. So horizontal motion is similar and we don't feel similarities, we feel differences in velocity. Fine. So I mean, when this passenger is here, stone is here. When the passenger is here, stone will be here. Passenger is here, stone will be here, because horizontally both will cover same displacement. Horizontal motion is similar. Okay. So path seen will be, see, vertical straight line, vertical straight line. When passenger is here, stone will be here like this. Is that clear? So this, we can safely get the equation of motion. In fact, path of stone as seen with the passenger in the train will be vertical straight line with an acceleration g down. Fine. And what if the train is also accelerating horizontally with an acceleration a and the passenger drops a stone? Okay, so when the stone is dropped, suppose the velocity of the train is u, even this stone will have the same velocity due to inertia of motion. Of course, this stone has nothing to do with the acceleration of the train, because once it's outside the train, it's falling freely under gravity. So acceleration is g down and velocity is u in horizontal direction. Once again, horizontal projectile like. So path of this stone as in with the person on the ground is going to be parabola with g down. But what about the path of that stone as seen with the passenger inside the train? Let's see. Now, okay, we know very well, if we are moving in a train with a velocity 10 meters per second, a stone will appear to go back with 10. If we are accelerating in this direction with a, it will appear that stone is accelerating back with minus a. Same way, if train is accelerating at a, it will appear that this stone, once it's outside, it will appear to accelerate in opposite direction with a and g in addition to that. G is already there. So it will appear as if this particular stone is having an acceleration of this much. I mean, under root this square plus this square is going to be root over a square plus g square, okay, at an angle theta equal to tan inverse a by g with the vertical. Fine, because you can take this a and keep it here. So this is theta with the vertical, tan theta is a by g, tan inverse a by g with the vertical. Fine. So this particular stone, as seen with the passenger in the train, will have an acceleration so much at so and so angle. But then one thing is clear, if the velocity of the train is u, even the velocity of the ball was u initially. I mean, when the stone is dropped, at that instant velocity, whatever velocity train will have, same velocity this ball will have. So initial velocity of this stone relative to train, initial velocity relative to train will be 0, and train is moving with a constant acceleration means, okay, stone will appear to have a constant acceleration minus a and constant acceleration g. Result of two constant accelerations also a constant acceleration, so it will appear to have a constant acceleration capital A. So acceleration is constant. U is 0, acceleration is constant. So path of the stone as seen with the person inside the train, as seen with the passenger, is going to be a straight line. We know when U is 0 and A is constant, path will be straight line. But that straight line will be in the direction of acceleration, in this direction. So, okay, it will appear as if, the moment you drop, it will appear as if starting from rest and moving with this acceleration, okay, at an angle tan inverse A by G with the vertical, in this direction, inclined direction, but path will be straight line. Fine. Now slight variation in the question. Suppose this train is accelerating horizontally and this passenger throws the stone down relative to the train, vertically relative to the train. What will be the path of that stone as in by this person on the ground and passenger himself? Let's see. So we know very well, at the instant of throwing the stone, suppose the stone is having a, train is having a velocity u, even stone will have that velocity u due to inertia. In addition to that, relative to train, you are throwing the stone vertically, passenger is throwing the stone vertically. Okay, so initial velocity of this stone due to inertia u and relative to train you are throwing vertically, that we suppose, so initial velocity will be something like this, as seen by this person. Okay, as seen by the passenger, person B on the ground. So, but then once it's outside the train, acceleration is g. This is initial velocity, acceleration is g. Initial velocity is not zero, acceleration is constant, but the direction is, other than, but the angle between velocity and acceleration is other than 0 and 180 degree. So path will be parabola, some parabola like this. Fine. Acceleration will be g down, but path is parabola, but the person is standing on the ground. Now, coming to the passenger himself, what he says. Okay, this passenger, it's very clearly mentioned. The stone is dropped vertically relative to the train. That means horizontal velocity will not be seen at all by this passenger. Whatever horizontal velocity the train is having, the ball is also having the same horizontal velocity. But with respect to the train, relative to train, vertical velocity is given. So initial velocity with respect to train or with respect to passenger inside the train is downward. Alright, let it be some v naught. And acceleration, once again the same thing. If train is accelerating at a, stone will appear to have an acceleration minus a and g in addition to that. So this will be the acceleration. Acceleration capital A, which is constant because small a and g are constant, means result is constant, and initial velocity is in this direction with respect to this person or with respect to train. Velocity and acceleration are not at 0 degree or 180 degree with each other, but initial velocity is not 0, acceleration is constant, path should be parabola. Okay, so parabola with acceleration what? A square plus g square at an angle tan inverse, this theta, tan inverse a by g with the vertical. At this particular angle, acceleration will be there and initial velocity is in this direction. So this type of parabola, but still parabola for this passenger as well, but a different parabola. Fine. Let us consider another case. Suppose a plane is flying with a velocity v naught at an angle theta above the horizontal, and if a passenger drops a stone from it, what will be the path of the stone as seen by the passenger himself? Let us see. Okay, so we know very well, whatever velocity the plane is having, initially the stone will have the same velocity due to inertia of motion. So initially relative velocity is 0. Velocity of the stone relative to passenger is 0. And acceleration of the stone, relative acceleration is obviously acceleration of the stone minus acceleration of the passenger, that is obviously g downwards. So relative acceleration is constant and initial velocity is 0. Okay, so obviously a relative path is going to be straight line. We have already seen whenever u is 0 and acceleration is constant, path will be straight line in the direction of acceleration. So relative acceleration is downward, so path will be vertical straight line as seen by the passenger himself. Okay, let us try to understand it in a slightly different way. We know in time t, we have already discussed similar cases. This plane will travel a distance after dropping a stone. Suppose the passenger is dropping a stone at t equal to 0 and t seconds later this will travel v naught t. Okay, if there would have been no gravity, even the ball would have traveled v naught t. But now because of gravity, v naught t plus half gt square, v naught t plus half gt square. The ball will have a displacement vector, initial velocity into t. This vt ut plus half gt square, we are using half gt square. Okay, so v naught t plus half gt square. Suppose plane is here, ball will be v naught t plus half gt square below, half gt square below. Plane is here, v naught t plus half gt square below. Okay, plane is here, ball will be v naught t plus half gt square. Plane is v naught t away, ball will be v naught t plus half gt square. So ball will be always below the plane, below the plane, below the plane, below the plane. So path of the ball as seen, or stone as seen by this passenger, is a vertical straight line. Okay, I have been replacing ball with stone, stone with ball, doesn't matter. Just understand, if it is ball, stone, stone. Fine.